Good afternoon and welcome to the American Floral Endowment's Grow Pro webinar series. I'm your moderator, Michael Wajasinga, and I'm a grower for Bell Nursery in Springfield, Ohio. I help oversee and manage the production of a wide variety of ornamentals for hundreds of stores across the country. Today's session is on technologies and strategies for sustainable substrates and containerized crop production. On behalf of the endowment, I'm excited to be part of AFE's Grow Pro webinar series that features a new topic every month presented by an industry expert. The webinars are free to everyone thanks to the generous support of AFE's sponsors. The views and opinions expressed in these webinars are those of the speaker and do not necessarily reflect the views and positions of AFE. As an independent nonprofit, AFE cannot endorse any specific product or opinion. If you'd like to learn more about our sponsors or are interested in becoming a sponsor for a topic, you can find that information on AFE's website at endowment.org/growpro. Today's session was pre-recorded in English by Dr. James Altland. After the presentation, Dr. Altland will join us for a Q&A. Feel free to submit your questions through the Q&A feature or chat at any time. We'll answer as many as we can before the end of the hour. Unanswered questions may be answered through a separate email exchange. This session is being recorded and will be shared to AFE's YouTube account. Through YouTube's accessibility features, you can access closed captions in other languages. To get us started, I'd like to share a bit about today's speaker. Dr. James Altland is the research leader for the Application Technology Research Unit. The unit focuses on agricultural spray technologies and all aspects of controlled environment agriculture. His specific interests are in chemical, physical, and biological properties of container substrates and how they can be managed and modified for sustainable crop production. Recent research has focused on chemical amendments to reduce the amount of phosphorus leached from containers. A major emphasis of current research is to better understand the biological properties of container substrates by documenting how management practices affect the microbiome. Using applicant sequencing techniques, they observe the change in microbial communities over the production cycle of crops exposed to different management practices. Dr. Altland, welcome and thank you for presenting today on sustainable substrates and containerized crop production.
Thank you, Mike. Today's presentation, I'd like to talk about some new substrate management techniques we've been working with in nursery and floriculture crops. I'd also like to talk about some phosphorus management techniques we've been working with. One of my colleagues calls holding your pea. Of course, we're talking about phosphorus and retaining phosphorus in the substrates. And finally, I'd like to talk about some of the problems we're having with peat and discuss some of the realities versus the imagined problems in terms of its environmental implications of using peat for horticulture. Growing plants in containers is not new. We have our first recorded instance of growing plants in containers that were inscribed on the walls at the temple of Deir al-Bahri in Egypt. These recordings go back about 1500 BCE. Throughout Europe, in the Middle Ages and the Renaissance period, plants were collected from all over the world and grown in conservatories and orangeries. In the United States, early in our history, plants were grown using mineral soil filled literally into cans or metal containers. The modern era of container production began in the late 50s or early 60s with this publication from the University of California, where they suggested growing plants in some combination of peat or sand, thus creating the first true soilless substrates. In the past 60 years, growing plants in containers has changed relatively little since the early 60s. There have been improvements in controlled release fertilizers and perhaps wetting agents, but still the principle of growing plants in containers using a soilless substrate has changed very little. One of the problems we have in growing plants when we fill these containers uniformly with the same substrate is we get a zone of saturation at the bottom of the container. In fact, several of my colleagues and I measured this several years ago, where we took a container, we saturated it, let it drain, then we froze it and sliced it into sections. And you can see the different volumes of water held in each inch deep layer in the container throughout the vertical profile. Typically, we have a zone of very saturated substrate at the bottom of the container, and it dries as we move to the top of the container. Because we have a gradient in water, we also get a gradient in pH, mineral nutrient solubility. And what we've just studied this past year is we get a gradient in the microbial communities that live in these different strata of the container. This happens because of the way water moves through a container. Typically, when we irrigate a substrate, the water enters the container and it branches and with preferential flow moves quickly to the bottom of the container. At the bottom of the container, it'll start to leach out of the bottom, and then it'll start to backflow up to the top of the container, slowly saturating back up to the container. And what we end up with is this, again, a zone of saturation near the bottom of the container with a fairly dry substrate at the top of the container. This is especially problematic when we first pot our plants because that small plug or liner is typically up here where the substrate stays drier longer. So I began working with some of my colleagues here, Dr. Jeb Fields at LSU and Dr. Jim Owen, who was at Virginia Tech but is now with USDA ARS. Chris Marble and Jeb's graduate student, Chris Crissione, on how we can fix the problems with this gradient in the container, how we can remove that zone of saturation at the bottom. And the story about how this started is rather interesting. If I remember it correctly, Dr. Owen was sitting in a lecture of a student working on bioretention systems. And you often see these in cities as rain gardens. But these are highly engineered systems that have a layer of fine substrate near the top that supports plant growth with a sand layer that supports nitrification of ammonium and urea in the nitrate. Then this internal water storage zone that will support denitrification of that nitrate into nitrogen gas, and then a drainage layer beneath that. As Jim was watching this presentation and looking at this slide in particular, he said, you know what, that looks a lot like a container. And he started to think, can we also layer substrates within a container that would perform specific functions and solve some of the problems we have with a typical container substrate? And that seems like a ridiculous notion at first, but when you look into it, other people are already stratifying their substrates, including green roof systems that use a growing media on the top layer with some filter cloth and a drainage layer beneath that with some other impervious layers. Turf sports also use stratified systems. And this is because the turf has to grow vigorously in all kinds of weather and be resilient to rough usage with cleats and athletics. And be able to drain and support that sort of athletic activity despite the weather. And if you think about it, planet Earth itself is stratified. If you remember some of your soils classes, we have an O horizon on the surface of the soil, high in organic matter, followed by the A horizon, and then the B and C horizons. In fact, it's possible that the only people on Earth that don't grow in a stratified substrate are nursery and greenhouse growers. So the team got together and we tried to develop a system that would fix some of the problems in containers. And what we wanted to do was stratify substrates within the container that would solve some of these problems. And the first thing that we attempted was fixing the problem of the water gradient by putting a coarse layer of substrate on the bottom with a fine layer of substrate on the top. And what this did, it would allow us to make the water gradient within the container more even. And if you look at this diagram, this shows what a typical substrate would look like, as we showed earlier, where you have a zone of saturation on the bottom and a relatively dry substrate near the surface. But when you stratify a fine substrate on top of a coarse substrate, what we get is at this where the two zones meet, we'll get what we call a transient water table, where that water starts to back up before it will drain into the coarser substrate. This keeps the surface of the container more saturated longer and with a more consistent moisture content compared to a conventional substrate. This was demonstrated by Jeb and his graduate student, Chris, down at LSU. I want you to focus your attention on these line charts on the right side of the screen. In a non-stratified substrate, this red line represents the water tension near the bottom of the container. And the more negative the tension, the more difficult that, or the more tightly bound that water is to the substrate. And so the more unavailable it is for plant growth. Now, at the bottom of the container, the substrates stay more saturated and more uniformly saturated over time. However, the blue line represents the water tension at the surface of the container. And you can see that the tension goes down dramatically after irrigation. It'll increase during irrigation and then dry every 24-hour period, and cycling back and forth between low and high tensions. Compare that to a stratified substrate, where again on the bottom, the bottom of the container has a relatively uniform moisture tension throughout across the days, but on the surface of the container, the tension also stays more consistent from day to day or throughout the hours of the day, without the wild fluctuations we see in these non-stratified containers. This chart shows plant growth establishment from 0 to 120 days after potting along the x-axis in a normally irrigated crop and a reduced irrigation crop, where we reduced the irrigation by 25%. And along the y-axis, we have the growth index of the plants. The blue line represents the growth curve of the plants in a control substrate, while the purple, green, and red line represents different stratification regimes. In particular, the red line representing a bark-peat combination on the surface of the container. These plants were able to establish more quickly, again, because the moisture content stayed more constant over time in those substrates. And what's notable is even in reduced irrigation treatments, those substrates that were stratified outgrew the control substrate with the higher irrigation rate. Another obvious application of these stratified substrates is putting all the fertilizer in the top half of the container. Dr. Owen did some work where he compared, using controlled release fertilizers, a full rate of fertilizer incorporated throughout the container versus 75% of that fertilizer, but in the top half of the container, versus 75% of that fertilizer top dressed. And you can see, because that nutrient is localized where that developing liner is at the surface of the container, those plants established more quickly and grew larger. Similar work by Jeb down at OSU showed that a 20% reduction in fertilizer in these three plants on the right with different stratification regimes were similar or outgrew the control substrates with the full rate of fertilizer. And this was a real interesting demonstration that Jeb did down with a petunia grower in Louisiana, where they took a very cheap and affordable pine bark substrate and put it on the bottom of the container with the premium peat-like substrate on the top to grow petunias. The major outcome of this demonstration research was to show that these petunias in the stratified substrate were far more tolerant of drought stress than those in the conventional substrate. And what the grower was primarily interested in was how much money he saved by replacing half of the substrate, the bottom half, with a very affordable pine bark substrate relative to the much more expensive peat-like substrate. So what we have learned so far is that establishment and growth in these stratified substrate is better. We can reduce the cost of fertilizers, reduce the volume of irrigation water, and we can dramatically reduce the cost of the substrate. But what I think is even more interesting about substrate stratification is once you open your mind to the idea that you don't need to fill the container uniformly with the same substrate, what other problems could you solve? This is, in my opinion, the biggest paradigm shift in growing plants in containers since we started growing in containers 60 years ago, because it opens up a whole new possibility of engineering substrates to solve very specific problems. We've heard anecdotes and stories about nurseries and greenhouses adopting this all over the United States and North America. Recently, Jim and I were visiting one of the largest greenhouse growers in North America to talk about substrate stratification and other research ideas. When we walked out, we found that some of their contract grown mums were actually grown in a stratified substrate, and again, using a premium peat-like substrate on top with a very coarse pine bark on the bottom. And what I'd like to point out is the vigorous root growth in these mums in that pine bark substrate that was unfertilized. And, you know, so we don't know the numbers of adoption, but there are nurseries and greenhouses that are adopting this technology. It is feasible. It will require some changes in your production or your potting system, but the ROI on this, because of the substrate savings as well as the fertilizer savings, should be a very short period of time. I'd like to switch gears a little bit to talk about fertilization and nutrient retention in substrates, specifically with phosphorus. Now, this is an example for nursery crops, but it holds true for greenhouse crops as well. A typical corn field would be fertilized with about 100 pounds of nitrogen per acre per year. We fertilize nursery crops somewhere around 450 to 600 pounds of nitrogen per acre. And I believe greenhouse crops would be somewhere equal to that. The problem is about 50% of the applied nitrogen and phosphorus is lost due to leaching because of the high irrigation rates we use. A postdoc of mine, Dr. Jake Schreckheis, he's now a scientist with USDA ARS in McMinnville, Tennessee, had an idea about how we can retain phosphorus in our substrates. And this is how it works. Our substrates, our organic substrates, whether you're talking about bark or peat-based substrates, they are inherently negatively charged. And that's due to the phenolic and carboxylic functional groups that are associated with the surfaces of organic matter. Because we have negatively charged substrates, they are very good at retaining cations. In fact, the cation exchange capacity of our substrates is actually quite high. The problem is they do a very poor job at retaining phosphates and nitrates. And phosphorus and nitrogen are the two most important nutrients in terms of promoting plant growth. They're also two of the most important nutrients in terms of their negative impact on the environment when they leach from containers. When phosphorus and nitrogen get into our surface waters, whether they're retention ponds, they can cause management problems in our retention ponds, in our irrigation ponds, but they can cause much more serious environmental problems when they leach into surface waters such as Lake Erie or the Gulf of Mexico or the Chesapeake Bay. So retaining more of the phosphorus and the nitrogen in those substrates has been a goal of researchers for decades. So Jake had an idea. What if we amended the substrate with iron sulfate? Now, I'll be honest, I thought this was a terrible idea when he started, but he turned out to be absolutely correct. When you amend the substrate with iron sulfate, the iron binds very tightly to organic matter. The sulfate leaches readily, but most of our fertilizers are sulfate-based fertilizers, so that's really not a concern, but the iron binds very tightly to the substrate. As a result, phosphate binds very tightly to the iron. And this is what Jake calls a ligand exchange or an iron phosphate bridge. So by amending the substrate with iron sulfate, we in essence magnetize the substrate to retain these negatively charged anions of phosphate. Unfortunately, this does not work with nitrate, but it will prevent a lot of the phosphorus from leaching from the container. So now we've done a lot of experiments, and I'm just going to show one. Jake has been working on this for several years now, and he's done multiple experiments in multiple types of substrates, nursery crops, greenhouse crops, peat-based, bark-based substrates. He's looked at binding rates of how much iron can bind to peat moss or pine bark, and then how much of that phosphate can bind to that iron. This is one experiment we've done recently with marigolds who are they're particularly susceptible to iron toxicity. So we wanted to make sure that the iron in these substrates was not going to be a problem. Now, of all the crops we've grown, we've never seen a reduction in growth as a result of amending a substrate with iron sulfate, but this would be an extreme example. Now, what we did was we amended all the substrates with 0 to 1 kilogram per cubic meter of triple superphosphate. For various experimental reasons, we decided to use triple superphosphate as a phosphorus source rather than use it in the water-soluble fertilizer. So along the y-axis, we have phosphate leaching. Now, the orange bar represents the phosphorus leaching from substrates that were amended with iron sulfate, and the blue bars, or the blue line, represents those substrates that were not amended with the iron sulfate. In the control substrates, we're leaching upwards of 500 to 700 parts per million of phosphate from the containers, while close to 0 from those amended with iron sulfate. And this continued to 4 weeks and 6 weeks. So we reduced the amount of phosphorus leaching from these containers by up to 95%. Now, plant growth was at the lower rates of phosphorus incorporation. We did see some competition with plant growth when we amended with iron sulfate. That iron bound too much of the phosphorus. But at a more typical use rate, there was no difference in shoot rate or shoot or root dry weight. And in general, we measured these plants in terms of their flowering, their foliar color, their chlorophyll content. All those parameters were similar as long as the, not at the low phosphorus rates, but at the medium to high phosphorus rates, the plants grew exceptionally well. And they did not leach any of the phosphorus. So this is kind of wrap up several years of research. If you amend these substrates, whether they're peat or pine bark based substrates, with between 2.5 to 5 pounds per cubic yards of iron sulfate, you can reduce up to 75. In nursery crops, is a little less because those plants grow longer and the phosphorus tends to overwhelm those iron binding sites. But in greenhouse crops, we can bind a lot higher percentage of the phosphorus. Now, iron sulfate's cheap. It comes in 50-pound bags. It has the consistency and texture of limestone. So this can be incorporated into very conventional and traditional substrate mixing systems. And it's cheap. It costs about the same as lime. So this is a very cheap, affordable, adoptable method for eliminating or dramatically reducing phosphate leaching from containers. I'd like to switch gears a little bit here now and talk about something completely different. And this is something that I've been working on for the past few months. It's the legal issues with peat. Now, in Europe, more than 50% of peatlands are degraded and less than 10% are considered to be in quote unquote good condition. And this has resulted in a lot of rules and regulations and laws in terms of banning or dramatically reducing the sale of peat in Europe. And there's a complete ban on all peat harvests in Ireland. Now, that has trickled across the pond to North America, and we've seen a lot of articles in the New York Times, Better Homes and Gardens, and even National Geographic, with rather incendiary articles about the problems with peat and how it has a whopping carbon footprint and the environmental issues related to using peat. And it made me wonder, because none of these articles, absolutely none of them, were supported by any quantifiable science. So I wondered, just how true is this? So we started to look into the numbers, and what I like to do is share what these numbers look like in North America. And again, this is a different issue from Europe. So 90% of the Canadian peat is sold in the United States, and 95% of the peat used in the United States comes from Canada. So what we're really talking about in North America is peat coming from Canada and being used in the United States. So let's talk about North America. There are over 280 million acres of peatland in Canada. Now, to put that into perspective, that's about twice the area of the state of Texas. 224 million of those acres, or about 80% of it, are in pristine condition. Now, Today, about 30,000 acres are being used to harvest horticultural peat. And in the past, there's about 43,000 acres total. So 73,000 acres total that are currently or ever have been used to harvest horticultural peat. That amounts to about 0.03% of the peatlands in Canada. And if you look at this pie chart, you notice the wedge that represents the peat used for horticulture, the peatlands used for horticultural purposes. It's so small it doesn't even make a line. It's basically a rounding error. Now, this other approximately 20% of the peatlands has been used for traditional row crops or housing developments, that sort of thing, but only 0.03% of the land used for horticultural peat. So the Intergovernmental Panel on Climate Change, this is a UN agency that does all the reporting on climate change for the United Nations. They estimated using very crude models and very poor data that approximately that a peatland that has been stripped and exposed for horticultural peat extraction will emit about 2.8 tons of carbon per hectare per year. Now, Dr. Hongxing He of McGill University used more sophisticated coupled heat and mass transfer models for soil, plant, and atmospheric systems. And he followed that up by doing on-site measurements of carbon emissions from these peat fields. And he more accurately measured that the carbon emissions from an exposed peatland are more like 1.5 tons of carbon per hectare per year. Now, to put that in perspective, how much carbon is that? That sounds like a lot. A single flight from Dallas to Chicago on a private jet, a rather small private jet, will emit over 4 tons of carbon into the atmosphere. That's a single flight. According to statistics, there are over 3 million private jet flights in the United States, not from Dallas to Chicago, but across the United States, over 3 million flights per year. So relative to the amount of carbon that's being emitted by just one human activity, private jet flights, the amount of carbon emitted by horticultural peat extraction is almost insignificant. But it's not zero. But let's look at some of the other implications of harvesting and using peat for horticulture. What is the carbon footprint of a cubic meter of peat moss? In terms of its kilograms of carbon dioxide equivalents per cubic meter. Well, different studies using life cycle analysis can quantify the amount of carbon emitted in every part of the process, from harvesting to mixing to packaging to shipping to using the actual substrate, and so that we can compare different substrates. Now, each study, when you do such a study, you have to make certain assumptions about where the peat is coming from, where it's going, how it's being transported, and how it's being used. So there are 3 different studies on this side, 3 different studies from 3 different groups of scientists, and comparing the carbon footprint of peat, ore, and perlite. And in some cases, we use rock wool. Different studies use different substrates. So, but a mineral substrate, just for comparison purposes. In each of these studies, well, in one of the studies, peat has a lower carbon footprint than core, but in the other studies, it is slightly higher. Now, when we look at other environmental impacts, and these are things like surface water and marine water eutrophication, soil acidification, land usage, land clearing, the environmental impact from peat compared to core is a lot less. And a lot of that is due to the retting process for harvesting core. So when you take that coconut husk, they try to remove the fiber from the pith. And what we use in horticulture is the pith. The fiber has other industrial uses that we're not concerned with. But in separating that fiber out, they have to use this process called retting, which uses a tremendous amount of water, and it can be quite damaging to the environment. So the environmental impact of peat is a lot less than core when you consider all these other variables. In addition, when we look at the human health impact, this involves all sorts of quantifying the carcinogens, the respiratory issues, the dermatological issues. Peat has a lower human health impact than core or rock wool. So when you look at these other scientific studies, the idea that we could just switch to another substrate and all of our problems would disappear is simply not true. And in fact, when you measure the environmental, the human, and the health impact of peat to some of these other substrates, it's actually less than most of these other materials. One of the arguments against using peat also is that you destroy the peatlands and that those peatlands could never be restored in our lifetime. And that's simply not true. When a peat bog would typically be harvested for about 10 years, some shorter, some longer than that. And when those peatlands are done being harvested, they use something called the moss layer transfer technique, which involves taking moss from living bogs and basically raising the water level and seeding that bog with these moss fragments. And what they've shown is after 15 to 20 years, a stable and very diverse community similar to a native peat bog will develop, and that bog will then become a net carbon assimilator. So in fact, that these peat bogs can be restored, and they can be functioning peat bogs that assimilate carbon from the atmosphere and store it in the ground, much like a native bog. And when you look at the actual land area of the peat, every year about 15 million cubic yards of peat is harvested. But when you consider the vast area of peatlands that are undisturbed, about 126 million cubic yards is being generated in native peatlands. So the peatlands are growing despite horticultural peat harvests. This chart shows the net ecosystem exchange of carbon. And if you look at this black line, this negative numbers indicate carbon is being sequestered. This is the black line represents the carbon sequestration from a native undisturbed reference peat bog. And the yellow, green, and purple lines represent the carbon assimilation from restored peat bogs that were restored about 14 to 16 years ago. And you can see that they are assimilating even more carbon than the reference bog. With air and everything, they're probably about the same. But in this particular study, they actually assimilated more carbon. The point is, these peat bogs can be restored to functional carbon assimilating bogs after they're done being harvested for horticulture. So peat moss, harvesting peat for horticultural purposes is sustainable. The carbon loss is minimal, and that carbon sink can be reversible once the bog is rehabilitated. But the question is, do we still need to harvest peat? And my answer is absolutely. And not only is it sustainable, but it's necessary. And just doing a little bit of math, an acre of harvested peat is enough peat to grow 27 million tomato seedlings. That will grow eventually 270,000 tons of fruit. So you could say peat moss feeds the world, or at least feeds part of us. An acre of peat can produce 3.3 million forest seedlings. That is enough to reforest 6,400 acres of forest land. Or it could grow 56 million ornamental, plugs for petunias, zinnias, geraniums, etc. So not only does it feed the world, it can reforest the world, and it beautifies the world. So peat isn't being harvested to fuel private jets and luxury cars. It's being used for very good reasons. And so, in my opinion, peat is not only sustainable, but it is necessary. And in case you were wondering, this was some work done by Charlie Hall and Dwayne Ingram 10 or 15 years ago. They look at the global warming potential of producing a single wax begonia in a 4-inch pot. And about 17% of the carbon footprint is a result of the substrate. So if you were to switch your substrate, and that substrate were so benign that you could cut the carbon footprint in half, well, you could save some of the carbon footprint of your ornamental crop, but not much. Most of it's still in the container and the tray, in fertilizer and pesticides and other things. And similar situation for a 3-gallon holly, about 8% of that carbon footprint can be attributed to the substrate. Now, in full disclosure, all the life cycle analyses I showed you were from Europe. We simply don't have that sort of data that has been generated in North America. One of the things that we're working on is doing the life cycle assessment for North American substrates. This would be peat harvested from Canada, core from Sri Lanka, pine bark and wood fiber from North Carolina, and then distributed and used in cities. And these are just 5 cities I just pulled out of, off the top of my head, but distributed to cities throughout North America. What does the carbon footprint look like and the human health impact and the environmental impact? What do those factors look like for North American substrates? And I believe, honestly, they would be similar to those other studies done in Europe, which would show that while peat is not environmentally free, so to speak, neither are these other substrates. And in fact, they would probably be very similar in terms of their impacts. So to wrap things up, looking at substrates and horticultural crops, stratifying substrates, we know the book has been written on this. It improves water and fertility use efficiency. Now, there are a lot of variables that go into that. And so Jeb and Jim and myself and our other colleagues are looking at how to maximize those variables to further increase water and nutrient use efficiency. But what other problems can be solved by stratifying substrates? When you open yourself up, again, when you open yourself up to that idea that you don't need to fill the container uniformly from top to bottom, what other problems could you solve? I'd also like to close in saying peat is absolutely sustainable. And, there are problems with using peat in terms of its harvest. Because of climate change, we're getting more summer rains in Canada, and that is limiting the amount of peat that can be harvested. So if market forces force us to use an alternative substrate to peat, so be it. So in closing, I'd like to acknowledge again the colleagues that I have, Jeb Fields, Chris Cristione, Jim Owen, and Jake Schreckheis, and their respective universities, of course, my employer, U.S. Department of Agriculture, Agricultural Research Service. And with that, I would like to take questions.
Awesome. Thank you very much for the presentation, Dr. Altland. We're going to go ahead and open up the presentation for questions now. So feel free to go ahead and add some extra questions through the chat feature or the Q&A as we start going through these. I'm going to go ahead and start here at the top. Erica Willis did mention that there was so much good information coming quickly, and I couldn't agree more. Just so everybody's aware, the presentation will be posted to AFE's YouTube account, and we have the link shared with everyone there in the chat. So I have a question here, Dr. Olin, by Abigail, asking if you tested the availability of phosphorus in the substrate where iron amendments were applied.
Yeah, so we're testing that in a number of ways, and especially just simply looking at plant growth and plant uptake of phosphorus in those substrates, because that's really the test. Now, we can do a number of different types of extractions on that media, but those only estimate what amount of phosphorus would be available to the plant. So the best way, as we say in science, is ask the plant. So what we'll do is we'll grow a variety of plants, and then we'll take the samples of the foliage, analyze them for phosphorus content, and they should be within a certain, recommended range. And so that's how we do that. And yes, generally speaking, as long as the phosphorus isn't low in the container, even with the iron sulfate, the plant can uptake the phosphorus. It is available.
Awesome. So I have a question here from Juan asking if you could talk more about the PhenoSpecs machine you used during the iron sulfate trial on the marigolds, specifically how this equipment helped capture data and how you would have done it in the past. And also if you could touch briefly on the cost of the machine and whether you've seen it being used in the field.
Yeah, so we built that in collaboration with Ohio State University. So we paid a part of that, and I honestly don't remember. It was very expensive. And what it does, you have to set the plants up very carefully. But once you get used to that system where you put the plants in a special order, you run that machine over the top, and within a minute or two, it can record the size and a really long list of spectral variables on the plant. So it can detect changes in color that the human eye can't detect. So you can evaluate plants and what they call phenotyping, just basically the physical appearance of the plants. It can measure flower numbers and size and density and the amount of branching. And, it takes some getting accustomed to. But it replaces a lot of labor that would go into hand measuring things and seeing, measuring how large the plants are and whatever. So from a research standpoint, or for those doing genetics research or plant trialing, or in industry, a lot of people are doing, cultivar evaluations, that sort of thing. It's invaluable to save time and labor.
Awesome. So I got another question here from Emmanuel asking if you have any information or idea on how to modify a conventional transplant line machinery to stratify substrates.
Well, I think the easiest way would be to add a second hopper. Now, what some people are doing is they'll run the plants through, or the containers down a conveyor once, bring them back around, and then run them down a second time. I think that the ROI on this would be, sufficiently quick that it would justify a second hopper and conveyor, or whatever disperses the substrate into the pot, whatever system you're using for that. But again, the simplest way is just run through this line twice, although that seems like a lot of labor to me.
Awesome, cool. And John, I'm hoping that answers your question. Another question popped up about how to fill pots with soil that is stratified with our current system of traditional pot filling machines if they need to change the machines. Like you said, maybe add another hopper or plan to run them through a second time, depending on how it works out with your labor budget.
Yeah, exactly. Yeah.
Cool. So a question here from Robert is the water table in the stratified container similar or different with sub-irrigation? That's a good question.
That's a really good question. And one of the things that we started with really is putting a coarse substrate on the bottom, or coarser substrate, like, pine bark, and a finer, like I said, more premium substrate on the top. So I'm not sure if this would work too well with sub-irrigation. And, I would, ask you to email me or reach out to Dr. Jim Owen, Dr. Jeb Fields. They may have already addressed that. I'm not aware of approaching it from that angle yet, though. So that's a really good question, and something that at least I'm not familiar that we've addressed that.
So a question here from Gerardo. He was asking if you could show the plot of marigolds start for the phosphorus again. I don't know if someone from the AFE team might be able to pull that up. But if not, at the very least, were they grown at low phosphorus rates? And he was kind of asking if the message is whether or not iron let me see. So the message is that iron bridges retain phosphorus from leaching, but is still available for plant uptake.
Yes. So we grew it everything from very low or zero phosphorus amended to very high levels of phosphorus. And when you have a moderate to high level of phosphorus, it will still prevent the phosphorus from leaching, but the plant will be able to take it up. When you get down into those really low levels of phosphorus, then you start to run into problems with plant growth. So, look, in nursery and greenhouse production, we typically, if we're using standard fertilization practices, we're applying an abundance of phosphorus. Although there's been a lot of research that's gone into lowering the rates of phosphorus that we use to be more conservative about the use of phosphorus, the practice is still we set our fertilization rates based on nitrogen, and phosphorus is just along for the ride. We have a 20-10-20. Whatever we set the nitrogen to, that's what phosphorus gets as well. So we're over applying phosphorus, and in that scenario, phosphorus won't be limiting even with the iron sulfate amended substrates.
Awesome. That was a great answer. So another question here from Brandon. Would you see a stratified technique utilized in smaller volume containers, or is it primarily being used in larger containers?
So we started on this just out of ease of research. We started in something like 1 to 3 gallon pots. I think we've gone up to 5 gallon pots as well. We have some of our colleagues down at the University of Florida who are very interested in applying this technique to plugs. And I don't know if I forget if I mentioned this in the presentation, but a lot of the emphasis on that is the belief that our plugs are overwatered in our traditional irrigation schemes with plug production, small plant production, or young plant production. So is this a way to increase the airspace in these plugs while still maintaining enough moisture? So again, some of our young plant colleagues down in Florida are really interested in that. I don't know that anything's been done yet, but that's definitely on our radar.
Awesome. This is kind of a personal question for me as a guy growing some plugs. Do you have any resources or anywhere to look for that kind of research as it comes out, or any recommendations where to find it?
Yeah, if you follow Dr. Paul Fisher and some of the work that he does and his websites, and he has some grower guides and all that sort of thing. Paul is one of the best in the research community at getting the research from as soon as it's ready and consumable by the growing public, he gets it out to you. So some of us are a lot slower than he is on that regard, but Paul's very good. And I would follow Paul and even reach out to him to see what he knows about it and some recommendation, because I know he's working on this issue of overwatering, irregardless of the stratification part. But how else can you manage those crops without overwatering and increasing the air the air volume in those small liners?
Awesome. Thank you. So still have some more time if you guys want to keep firing away some questions. I have a few more left here. So when stratifying the substrate layers, do you have a recommendation on how deep or what percentage each layer should be?
Yeah, Dr. Jeb Fields at LSU recently done some work with that, and I'm going to paint this with a very broad stroke. But about 50-50 in terms of fill the container up halfway with one thing and then halfway with the other. When you went more than that, so like let's say you tried to fill it up 75% with that cheap, coarser substrate, we started to run it, or I think the research showed that the plants started to suffer a little bit in that. And if you went lower than that, it really didn't help anything. So 50-50 seems to be the sweet spot. There's still a lot of work to be. That's one of those variables we still need to optimize under different scenarios and different conditions. We started 50-50, we had to start somewhere. So we started there. It worked really well. But when we went up to 75-25 or 25-75, sometimes it wasn't as good and sometimes it didn't help. So 50-50 seems to be the sweet spot.
Awesome. Sweet. All right, so we got one more question here. Does amending the substrate with iron sulfate affect the pH?
It absolutely does. And anyone who's worked with iron sulfate knows that will drive pH down a lot. So what Jake had done early on is he countered that with an additional allotment of dolomitic lime, which we all use to raise the pH of peat and bark-based substrates. And when you do that, not only do you stabilize the pH right in that 5 to 6 range, but you would sequester even more phosphorus. Calcium and magnesium carbonates will also bind phosphorus, not as efficiently, not as much, but it does help. So it's like a win-win. You adjust the pH and you hold on to more of that phosphorus. So that was a very fortunate and very easy solution to that pH problem. But yeah, don't use iron sulfate without lime. You're going to have some pH issues if you do that.
Awesome. All right, I got our last question, and then I think we're going to wrap up. So how many layers of substrates can be added in a container to get maximum benefits of stratification?
Well, what we've worked with so far is 2 or maybe 3. And some of the work that Chris Marble from the University of Florida and I have worked on is a coarse layer on the very top, and a fairly small one, about 1 inch deep, to limit or it dramatically reduces the vigor of germinating weed seeds. Now, this is more relevant in nursery crops. In floriculture crops, you don't often have the plants around long enough to worry about weeds. And, in the greenhouse, you're probably free of most of those issues. But in nursery crops, where you're outside several months, that can become an issue. So a very coarse layer on top, and then, the tradition, the fine layer on the top, the topmost part, and then the coarse on the bottom. So we've gone as high as 3, but again, looking at 1 and 3 gallon pots. So the smaller your pot, that might become logistically a little difficult.
All righty. I think we're going to go ahead and wrap up. We'd like to thank you, Dr. Altland, for the wonderful content today and the great presentation. I know I got
Thank you very much.
a lot out of it. And I'd also like to thank everyone else for joining us today for another session of AFE's Grow Pro webinar series. I'd like to welcome everyone to join us next month for Dr. Melissa Manew's presentation on biorational products for botrytis control on Tuesday, January 16th at 1 p.m. Eastern Time. You can go ahead and pre-register at endowment.org/growpro. And while you're there, check out our past webinar recordings, including this one, other grow-related resources, and research reports available to you for free, thanks to industry support. This concludes the end of our 2023 Grow Pro webinar series. And if you found these webinars to be valuable, we encourage you to donate to continue supporting research and educational resources like these. The link to donate will be posted in the chat below. We have also recently released the new schedule for 2024 Grow Pro webinars, and we encourage you to check them out and register ahead. We ask that you please complete the brief survey about today's session, where you can suggest additional topics and help us continue to improve these webinars. Thank you again for joining us, and have a great day.